Hello and welcome to another Reigate Maths video. This video will focus on the second year content from the Decision 1 unit for the further maths, looking at the introduction to Floyd's algorithm. So what we're going to do in this video is introduce kind of the point of Floyd's algorithm and go through the algorithm itself. The second video in this two-part series will be going through an example of using that algorithm, both how to implement it and then how to use your final answer to find what you're trying to do. So what is the point of Floyd's algorithm? Well, Floyd's algorithm is actually very similar in purpose to Dijkstra's algorithm, but it does have one key difference. Floyd's algorithm finds the shortest distance or the shortest weight or shortest path between each pair of vertices in a network. That's what it does. Okay, so remember, Dijkstra finds the shortest path from one vertex to everywhere. They do the similar but slightly different things. Now, for the purposes of the exam, you do need to know both. You don't really need to know the benefits of one over the other, but hopefully by going through Floyd's algorithm, you'll see when one's useful, when's the other. So Floyd's algorithm is great for really small networks, and it does find the shortest distance between every single pair of vertices, where Dijkstra's only finds one to everything. Dijkstra's is a lot quicker though for bigger networks, at least to do physically by hand. So that's kind of the point of it. So let's look at the algorithm itself. So the algorithm is quite lengthy, so we'll take it through in a few steps. As I said, the next video we will look at an example. So if you just want to see how it's implemented, jump straight to that video. Otherwise, this is really useful to kind of understand what's going on. Okay, so the first thing you do is you complete an initial distance table for the network. And what you put in is the direct connections. So if it's not the shortest path, that's what the algorithm finds. So if you can see that A to B has length 10, but if you go A to C to B has length 9, in this part you're still going to put the 10. If there is no direct connection, then you put an infinity sign in as the element in the network, or sorry, in the matrix. What you then do next to it is you form an initial root table. So as you go through the algorithm, what the distance table will do is we will change the distance table in every iteration. We will also change the root table at the same time in the similar way. So what this will do is it will simultaneously find not only the shortest distance, but also what the path is to some extent. Okay? We'll look at how to do that in the example because the description's a little clunky. Okay, so for the first iteration, you copy the first row and column of distance table into a new matrix. And then you lightly shade that. Okay, you lightly shade it in. The shading is important. It's actually part of making sure you are comparing everything properly. So you then continue the iteration and you consider every unshaded position. If the sum of the two shaded points is greater than the number that exists already, then you just copy existing number down. If it is less than, this is also or equal to. If it's less than, then you copy the sum down. What I mean by the two shaded points, so we'll have our grid like this, and we'll have shading looking like this. So if we're considering, say, this box here, we're going to be looking at the sum of these two numbers. And that's what I mean by the shaded points compared to the unshaded position. Once you've done this for all of them, the iteration 1 is complete. Iteration 2 is you repeat the process using the table you just got here, but instead of doing the first row and column, use the second row and column. The other thing you'll do here that I just forgot to mention is you will then change the letter in the root table. And again, I'll show you how to do that when we look at the example in the next video. You continue until all rows or columns are done. So if your matrix is a 4 by 4, you're going to have 4 iterations. If it's 5 by 5, you'll have 5 iterations, and so on. Okay, each new iteration, you're using the previous tables that you've just got and that row and column. So iteration 2 is the second row and column, iteration 3 will be the third, and so on. Okay, so if it has n vertices, it takes n iterations to complete. That doesn't mean it's got order n. The order will be much more than that, but you know how many iterations you'll have to do. Now, quite often, the tables that you will be filling in are given to you in an exam. Okay, so you don't have to sit there drawing out a bunch of tables. Quite often as well, if they want you to do Floyd's algorithm, the maximum size of a network they'll do is really 4 or 5. Okay, they're not going to get you to do it for much more than that, because at that point it's just repetition. Now, the other thing that Floyd's algorithm does much better than Dijkstra's algorithm is it deals with negative weights and directed networks a lot better. So it has its bonuses, but as you can see from here, repeating the process for however many vertices you have is very lengthy, whereas Dijkstra is a lot quicker, but it only does one specific thing. So this is kind of a brief overview of what the algorithm is. In the next video, we're going to be looking at an example using this algorithm on a 4x4 matrix. Thank you for watching.